Yeah, good morning to all of you. In the previous lecture, we have obtained the expression of h for a given L, and in that case, our L is time independent. Now, in this lecture, I will solve or I will discuss the expression how to obtain the expression of h for a given L, and L is time dependent. So, if we have an expression of Lagrangian or the time dependent Lagrangian system, so the time dependent Lagrangian system is simply L equal to e to the power nu t, where nu is any constant, mx dot square by 2 minus kx square by 2. So in that case, what is our h, or what is profile of h and equation of motion and corresponding Hamilton's equation of motion. So in this case, in earlier case, our L is time independent. In this case, our L is time dependent. So how to obtain the expression of h for a given L? So we know that the relation between h and L is simply h qk pk and t, which is equal to summation of this k pk qk dot minus L, which is function of qk dot and t. See, Lagrangian is function of generalized coordinate, generalized velocity and t, and h is only function of generalized coordinate and generalized momenta and t. So in this case, our L depends upon qk dot and t. There is time term and there is a generalized velocity and generalized coordinate term also. So with the help of this relation, we can easily set up a Hamiltonian expression. So how to set up, or what is our next step? Our first step is write down the relation between L and h expression. Second, using the concept. So this is 1, this is 2. Now replace all qk dot term by pk. So these are the steps through which we can convert our L into h. And third, now applying the concept of generalized momenta. So these are 3 steps. Step 1, write down the expression of L, which is in generalized coordinate, generalized velocity and time. Then write down the relation between h and L. So this is the relation between h and L, and this is very important relation, because with the help of this relation you can find out the expression of h for a given L, and converse is also possible, because we can find out the expression of L for a given h by rearranging this expression. So write down the relation between step 1, write down the relation between h and L, then replace all qk dot term. This qk dot term means this is generalized velocity term. It could be anything, that is why it is known as generalized velocity. I have already explained the meaning of generalized velocity. In this case, our generalized velocity is x dot, and in earlier example our generalized velocity is x dot and y dot, because we have two generalized coordinate. In this case, we have only one generalized coordinate. So replace all qk dot term by pk and apply the concept. How to replace? How we will replace this all qk dot by pk? using the concept of generalized momenta, which is del L upon del qk dot is simply pk. Now with the help of this mathematical tool, we can replace all qk dot term by pk in order to find out the h expression. So in this case, what is our qk is simply here, our qk is simply x, small x you can write it as. This is x. So we have, what is our del L upon del x dot? So differentiating partially with respect to x dot. So we have only one x dot term. So which is mx dot. Mx twice mx dot by t. So del by del x dot e to the power nu t mx dot square by 2 minus kx square by 2. This is constant, this is constant. So if we are differentiating, since we are differentiating partially with respect to x dot, so it will give, this will 0, this will give twice mx dot. So this will give twice mx dot by 2. So this will cancel out. So what we have, and this is constant term, we can take it outside. So we have e to the power nu t mx dot del L upon del x dot, or, and what is del L upon del x dot? So del L upon del x dot is simply px. Del L upon del qk dot is pk. So in x we have px, and what is the value of this? This value is this one, e to the power nu t mx dot. So this implies that what is our x dot? X dot is simply px by m e to the power, this will go down, so this will becomes minus. So this is the value of x dot. So now we have expression of x dot in terms of px. So with the help of this generalized momenta concept, we can replace all x dot by this term, where now from this equation, now we have a relation. So this is, so h is simply our pk qk dot, because our k is simply 1. So x, so no need to expand, because our variable is, we have only one running index, we have only one generalized coordinate. So this expression is becomes simply px x dot minus l, and what is l? E to the power nu t mx dot square by 2 minus of kx square by 2. Now our c, this is the final expression of h, but in this expression our h is having h is function of generalized velocity and generalized momenta and time, but our h is only function of generalized coordinate, generalized momenta and time. So anyhow, if we will replace this x dot term by this term, so what we have now, from, let me, this is 1, this is 2, and this is 3. So now putting the value of, x dot, so what we have, px, this x dot is px square by m e to the power minus nu t, minus e to the power plus nu t m by 2 e to the power, this px is, x dot is this, so square of this is px square by m square e to the power minus 2 nu t minus kx square by 2. So rearranging e to the power minus nu t, px square by m, and this is e to the power nu t, this is power e to the power minus nu t, so minus plus becomes minus, so we have one more additional term e to the power minus nu t. And what about this? This is simply this m will cancel out, so we have px square by 2m plus this minus becomes plus kx square by 2 into e to the power nu t, because this is e to the power nu t, this is minus nu t, so if this term goes inside, so this minus plus becomes minus, so we have this term and this is this term. So this is px square by 2m, this is px square by m, so 1 minus 1 by 2 is simply px square by 2m e to the power minus nu t plus kx square by 2 e to the power nu t. Now this is qk, pk and t. Now in this expression there is no generalized velocity term, or Hamiltonian. So this is the correct expression of Hamiltonian, because in this we have only generalized coordinate, generalized momenta. So we have generalized coordinate, generalized momenta and time. So our h is basically function of generalized coordinate, generalized momenta. Otherwise because this is not the correct expression of h, mind it, this is the correct expression of h, because our h is only function of generalized coordinate, generalized momenta and time, but here we have generalized velocity term. So anyhow we have to replace all qk dot term, all generalized velocity term by generalized momenta using the concept of del L upon del qk equal to pk. So this is the way to find out the Hamiltonian expression for a given time dependent Lagrangian. Now what is Hamilton's equation? So what is del h upon del qk, which is del h upon del x, which is minus pk dot, which is px. So del h upon del x is simply kx e to the power nu t. This is del h upon del qk, or del h upon del x is this. What is del h upon del pk, which is qk dot, which is x dot, and what is del h upon del pk means differentiating this Hamiltonian partially with respect to px. So we have twice of px, 2 will cancel out, so we have again px by m e to the power minus nu t. Okay, e to the power minus nu t. And what is del h upon del t? See, del h upon del t is minus nu px square by 2m e to the power nu t plus nu kx square by 2 e to the power nu t. So in this case our h is del h by del t is not equal to 0. So h is not constant of motion. So we cannot write h equal to. So in this case h is not equal to t plus v. This is not non-conservative system. So h is not a constant of motion. That's why we cannot express our Hamiltonian in terms of total energy, that is sum of kinetic plus potential energy. So corresponding to 1L we have three different sets of equation of motion. We have three sets of equation of motion. So corresponding to one Lagrange equation of motion or one generalized coordinate, we have only one generalized coordinate, we have only one L. Corresponding to one L expression, corresponding to one L equation of motion, we have three different sets of equation of motion. If we have an equation of motion in Lagrangian, so correspondingly we have 2n plus 1 sets of equation of motion in Hamiltonian dynamics. So in Lagrangian dynamics, if we have one equation of motion or n equation of motion, so in Hamiltonian dynamics, see, if in this dynamics, if we have n equation of motion, so in H dynamics we have 2n plus 1 equation of motion. This is another very important statement question. This is very important statement questions. The corresponding to that n Lagrangian equation of motion, how many equation of motion in Hamiltonian dynamics? So simply we have 2n plus 1 equation of motion, because we have one generalized coordinate in this Lagrangian, so we have one Lagrange equation of motion. So corresponding to one Lagrange equation of motion, we have three different sets of Hamilton's equation of motion. So it's all about this dynamic. So in this example, with the help of this example, we can understand that how to set up a Hamiltonian or Hamilton's equation for a given time dependent Lagrangian. And I think it's all about this example. Thank you.